Let's look at actually solving the volume of a ice cream cone. Actually, this problem is slightly different because in a previous example, we had sort of a spherical little portion above. In this example, let's say what we would get if we actually took a full sphere on top of that ice cream cone. So we loaded it up a little bit more. And in this case, let's just look through the example. It says 11, use spherical coordinates to find the volume of the solid that lies above this specific cone and below this specific sphere. Assuming constant density K, let's also consider what would be the centroid of the region. And we have a nice diagram here as well. I believe this example was also solved in your textbook. So if we go a little bit too fast here, you want to look more in detail, you can go through that one in your book as well. But essentially, one observation to note is that the conic, again, how we would have written this in chapter 12 was z squared equal x squared plus y squared. Notice actually the top half of a cone, because typically a quadric surface cone actually is a double, has both the top part of the cone and the bottom part, kind of like our hourglass shape. But when we just use the positive variant of the square root, we just get the top half of the cone, which, like in the last example, this actually translates directly to phi, because this would be a 45-degree angle formed with the z-axis. So in this case, phi will actually just go between 0, the z-axis, and pi over 4. Similarly, theta will go 0 to 2 pi because we're doing our full circle here. And the last component is, well, what about rho? Well, rho is not as straightforward as going from 0 to 1 because our sphere here is actually not centered at the origin. It's actually been moved up by 1 unit. Or we can again see this equation of a sphere centered at, the center of the sphere would be at 0, 0, 1 half. And its radius would actually also be 1 half because of the minor shift. But as we can do often, instead of trying to think about all those little details, we could just take our equation and convert it into spherical coordinates, because this is essentially going to be the top part of our object. So let's go ahead and get our integral going and set up as we try and solve this problem. Okay. So we'll have our triple integral across region E of 1 with respect to dv, because reminder that the volume of region E is always solvable by using the triple integral of 1. And all that being said, again, we can think about this integral in spherical coordinates. What's nice is, again, 1 will just be 1. We don't need to worry about changing 1 because that doesn't change. But dv will need to be translated into terms of rho, theta, and phi. So again, with our Jacobian, we have rho squared sine phi multiplied by d rho, d theta, d phi. And one thing to always think about is the ordering here, because with x, y, z, r, theta, there's kind of our typical ordering. But what I would recommend is, like with cylindrical coordinates, is to follow the typical order, because I would say 9 times out of 10 we're not going to think about even messing around with that and changing the order of integration. And in this case, given that it's a fairly simple integrand, not really necessary to even waste our time thinking about. Anyways, again, with our boundaries, however, as I was saying, theta and phi are directly just based on angles. So phi is just varying from 0 to pi over 4 because we have that cone which is balanced in x and y at a 45-degree angle. Let me make that a little more clear. That should be a 4. Sorry, the program that I'm using here is a little harder to write clearly. Let's get that more clearly. Okay, perfect. And then again, theta will go from 0 to 2 pi because we're going through the whole circle. And then the last question is, okay, well, what is rho? Because rho is not just 0 to 1 here. We have a much different scenario. But that was kind of my point about we have our equation here, and this equation can be translated into our coordinates. Because if we look at the left-hand side, we have x squared plus y squared plus z squared. But by our fundamental transformation, x squared plus y squared plus z squared is just rho squared. because you could plug in rho sine phi sine cosine theta and all that jazz for xyz to translate any rectangular format into polar form. In this case, it's a little bit more direct because the left-hand side of this equation is just rho squared. And z, reminder, if you aren't certain of yourself, you can always just go back to your formulas. Z is rho cosine phi. So what we actually have here, if we translate this to our spherical coordinate system, is a almost seemingly simpler equation. Rho squared is equal to rho cosine of phi. And if rho were not 0, in this case, we're actually letting that be our lower boundary of our starting point. But we could divide both sides by rho, and we get rho is equal to cosine phi. But essentially, this gives us an upper bound on our sphere here, because we'd be starting at a 0 position where there is no radius and going all the way up to cosine of phi, which represents kind of the upper shell, the top of the ice cream cone. And so sort of summarizing here, we want to integrate from 0 to rho cosine phi, and this will give us the volume within our ice cream cone. Okay, so now let's start progressing through the integral. And noticing, the interior boundary is a boundary on rho. So in this case, we can't separate them into 3 as we did last time because we have components within our boundary. Oops, I wrote a rho there. There's not supposed to be rho there. It's just rho is equal to cosine phi. We're going from 0 to the upper part, which is just cosine phi. There, now that makes sense. All right, so starting with our most interior integral. So leaving the first 2 on the outside. On the inside, well, we're going to be integrating rho squared with respect to rho. So we're going to have rho cubed over 3. And again, our sine phi we're treating as constant because we're doing the iterated partial integral here. Rho cubed over 3 sine phi evaluated from 0 to cosine phi. And then this will be multiplied by d theta d phi. And now if we plug these parts in, so cosine phi will become cubed and 0 will just be 0. So writing this all out again, from 0 to pi over 4, 0 to 2 pi, and we're going to have cosine cubed phi sine phi over 3. And we can probably even pass that 1/3 through our integral. And this will give us the next few parts. Now this part we could separate out, but notice that since this function does not depend on theta whatsoever, the antiderivative of theta with respect to theta, or of 1 with respect to theta, will just be theta, evaluated from 2 pi to 0, but this boundary will essentially just give us 2 pi to 0. So let's just do a quick shortcut. We're going to have 2 pi over 3 for the secondary integral. And then finally, we can process our integral with respect to phi, which, like in the last video, we can use looks like a u substitution will work just fine right here, right? And it's been a few years since I looked at this example, so sorry I'm a little slow. But if we set u to be the cosine phi, then du would be negative sine phi d phi. And then we can multiply both sides by our negative here to change our boundary from sine phi d phi into negative du. And so we'll have a negative u cubed here. Let's write that all out. So we'll have 2 pi over 3 integral of u cubed times negative du. And again, we want to change our boundaries here because cosine of 0 will be 1. And cosine of pi over 4 will be root 2 over 2. And notice that our boundaries look reversed as what happened with our substitution, but since our u boundary was negative, again, tactic we can always do is we can change the sign on our du and flip our bounds. So swap where these are, let's erase those, put the 1 on top and the root 2 over 2 on bottom. But As usual, this is tactically what I'll always do when I get a negative du, because it's essentially flipping our bounds. And so let's flip that to where it will make our life less negative, right? We always want to be positive, be optimistic in life. Okay, so let's finish this on up. So integrating u cubed, this would just give us u to the 4th over 4, evaluated from 1 to root over 2, and then we can finish up our math to see what our volume here would be. And so plugging this all in, we're going to have, so just 1/4 to start with. And then when we plug in root 2 over 2, this is gonna, when you square root 2 over 2, you just get 2/4 or 1/2. So this is actually just going to be 1/2 squared, which is 1/4. So we have 1/4 over 1/4, or sorry, 1/4 divided by 4. That all should just be 1/16, assuming my mental math is doing okay here. And 1/4 minus 1/16, this should be, if I multiply this by 4, I'm going to get 4/16 minus 1/16. So this should be 3/16. So I have 2 pi over 3 times 3/16. And the 3's we can cross cancel. The 16ths would simplify, and this would leave me with pi over 8. And after all this work, I sure hope we got the right answer here. I don't remember what it should be, but this seems like a reasonable result to me, as we're finding the volume within this little mini ice cream cone that's starting at 0 going up to 1, and it's bounded in between, you know, a rectangle that's, you know, 2 by 2 by 1. So we should be expecting to have a fairly small volume here, which again, that will be in cubic units. And our example says, you know, if we assume constant density, can we find the centroid? So say we wanted to spin this ice cream cone around an axis or whatever. Let's not go through that in this video. I'll leave that as an exercise for you to try for yourself. But essentially, triple integral is very useful, because if we integrate across 1, we can find the volume of any region E, as long as we know how to bound it. And then we can also go beyond and say, what is its moment of inertia, center of mass, all that good stuff that we talked about. And summarizing, with spherical coordinates, I can make a lot of integrals, maybe not a lot, but certain very specific types of problems a lot easier. Often those involving cones and spheres, and equations that involve all of our variables cubed and so on. Anyways, in the next video, we'll talk a little bit about how can we generalize change of variables, and why is our change in variables in that problem rho square sine phi.